So, yeah, I'm Henrik, and I did this paper together with my senior engineer, Dr. Friedemann. The topic is a didactical approach for the training of virtual reality, and this is what I would like to talk about today. First of all, I would like to give a little introduction. So what is the problem that I'm actually going to solve, or which I'm going to partially solve? I'm going to explain what the target is of the paper, and I will then derive a theoretical concept. This concept will include what the software should look like that I later programmed. I'll give you a little video of the software, and then last but not least, I'll give you the results of the experiments I did with the software and just show you what the benefits are. So, the introduction. So, we're from Germany, and in German construction industry at the moment, we have a very high amount of seasonal workers. So by definition, these seasonal workers do not have the same experience as a full-time employee of a company. And so they are rather low qualified in comparison with other fully employed persons. And this kind of leads to a high demand for the qualification. So basically what we're doing right now is that supervisors or more experienced worker work together with a trainee and show them how it's done. This results either in the supervisor has less time to do his own work, or if he does not spend that much time in supervising, the trainee will make mistakes or he will even hurt himself. So, and then at the same time we had several presentations today and yesterday. We have virtual reality, which is kind of a promising technology. And we could use that for training assembly tasks in this construction industry. So this paper is not yet about comparing other technologies. We did that in later future works. It's just about getting to know of how software for these kind of trainings should look like. But at the moment, there are virtual reality trainings for these tasks. But the problem is that whenever you have a new task that comes in, basically what people do is they do completely new programming. And we want to avoid that. So we want to take down the costs, take down time to initiate such a training by implementing a software that can be taught the scenario fully immersive and without programming knowledge. Then usually if there are some software for this purpose, they do not have a very clear didactical approach, and if they do have, they are normally not quantified. So what is the target of this paper? I want to establish a VR training concept for the cognitive aspects of assembly tasks in construction industry. That training concept should require only a reasonable effort, meaning that I do not want a programmer to do a new training setup only because I have new CAD data or new BIM data. Secondly, it needs to be adaptive, meaning that if there's a trainee that is more experienced than another one, I want him to get a harder training. And third and fourth, the software or the concept should be tested and it should be quantified. So this is basically what I'm going to do. For the theoretical concept, basically I do two things. First of all, I'll define the learning sequence, which I would like to improve later. And then I'm going to derive some didactical principles that I put on this sequence and derive some of the concept of how the software should look like. Okay, so for the learning process, what I understand in this paper as the learning sequence that I would like to teach with VR. First of all, the worker receives any kind of information that can be orally, that can be written, but it's usually some kind of information like move a part A in a place A to a part B. Then the second step is that the worker identifies the component wherever it is. Then he identifies the final position, and last step is he executes it. So that is one sequence, and usually the training scenario is set up with multiple sequences that have to be memorized. So how is that implemented in a standard VR approach if you do not have any programmers available? You have to give him some kind of information, okay? So the easiest part is just to put in a list with written instructions. No programming involved, no big deal. Secondly, you leave the worker alone and he is searching for the part. He's searching for the final position and he's then executing the step without getting any feedback, because feedback would have to be programmed. So this is basically the standard approach that I compare my own approach to. So later when we see the results, this is what I call the standard approach or the opposing concept. So now I got my approach. This is based on a prototype that I actually explained in an earlier paper. But the basic concept is that we have a trainer come in the virtual reality, and he is basically executing the entire training sequence one time. And the software records anything it needs. Meaning it needs the part, the tool, the final position, original position, or even hints or warning signs, whatever it needs for this training session. And then when the worker or the trainee when it's the turn of the trainee, he gets all these information whenever it's needed. So for this paper now, I have enhanced this concept by this, what I call the didactical approach, with 5 levels. Actually, it's just 3, because level 0 is more like a presentation mode. It's not very active. It's more people can put on the VR glasses and just animate anything, can just get a glimpse of what it's like. It's not really training. And level 4 is not really training either. It's more evaluation. So it's the final test whether the trainee understood or did not understand the training. So I already said level 0, that is basically animating a part whenever I press a button. Level 1, the training starts to be a little more active, meaning that the trainee gets all the information he needs. In this case, the easiest part. Usually this is indicated by blinking of the part that has to be moved, and a shadow of this part blinking wherever it has to be moved to the final place. The tool that has to be used is usually placed in the hand of the trainee, so all the trainee has to do is move the part. Then it gets a little trickier. The identification of the component is not supported by the software any longer, meaning that this is some information that now the trainee has to know. So basically he has to memorize what part do I have to move. But the rest, the tool and the final position is still indicated. And then level 3, this is the hardest part. Neither the tool nor the part nor the final position is indicated, meaning that by now the trainee should have memorized everything. We still have some kind of control mechanism in place. That means that once the trainee grabbed the part, moved it close to the final position, there's a little threshold that I find, the object will snap in, so that I avoid these tricky things that is not really part of the training task to place virtual objects where it belongs, but it has to be close. Yeah, so that is how the software is supposed to look like. And yeah, just to make it easier to imagine, I have this little video. This is just level 1, 2, and 3. And this is, yeah, with the Lego. So this, I'll explain later. This is level 1, so you see both parts are blinking. Not very hard. Level 2, it's just the final position that is blinking. The tool is always the standard controller. And level 3, neither one is blinking, neither the final nor the original position, but you see the object is snapping in, so we don't have to do fine adjustment as a training. This scenario is just for demonstration, so of course this is not a real working task of construction industry. But this brings me to my evaluation. I have derived the concept, I've put it into software, and I want to put it into action. And I had kind of the problem that if I go into real construction tasks, it either gets too expensive to repeat the training, it gets too dangerous for the trainee, or we didn't even have the material to do the training. So since I only focused on the cognitive aspects of this training, what I did is I took these plastic Lego bricks and then I'll carry out the experiment with these two scenarios, and then later derive or hope that I can take these results to the reality. So what is the question of the experiment? It's the one and only question: does the new approach offer any benefits? Again, this is in comparison with the VR standard approach that I explained earlier. The procedure, we have two scenarios, scenario 1 and scenario 2, that are equally hard for the trainee, that have to be memorized. And we have two groups. Each group is getting one scenario and have to set it up for 3 times in the virtual reality. Meaning with the VR standard approach, they have 3 times to build it. Meaning with the new My approach, we have level 1, 2, and 3. While doing so, the trainee may take as much time as he likes. And whenever he says stop, that's it. Okay, so no time pressure here. And after he's done in virtual reality, he goes back into reality and shows me whether he has learned or whether he did not. So he's actually building these two scenarios. The measurement that I took is, first of all, the duration of the training, defined by the trainee. Then, after the experiments, I asked the students to grade my software and the other software. And these are the ones that I found significant effects on. So these are the ones I'll go into detail in the next 2 slides. And the other 2 measurements, I took the duration of the execution in real life, and the mistakes made in real life did not show any effects. So basically they were the same. Not the same, not really the same, but close enough to be same. So for the evaluation, on the y-axis you can see the duration of the training in seconds, and on the x-axis the participants. So as you can see, we have a number of 10 participants. The darker bar is the standard concept, the opposing VR concept, and the lighter one is the training time with my concept. As you can see, the average dropped from 710 seconds to 256 seconds in the training time, which indicates that there is a good effect. I did a paired one-tailed t-test with an alpha of 0.05, resulting in a critical value of 1.83 and a t-statistic of 8.68, which leads to, or which now I may conclude that with a 95% probability, we do have a significant effect when using the, my concept contrary to the opposing concept. For the motivation, again, on the y-axis you can see the grading points. It's a scale from 0 to 15 points max. On the darker columns are, again, the opposing concept, the lighter one is mine. So you can see that the motivation when using my concept rose from 5.2 to 12.4 points. Again, I did a paired one-tailed t-test with an alpha of 0.05. Critical value again is 1.83, and the t-statistic in this test is 6.9, which again leads to the conclusion that with a 95% probability, we do have a significant effect when using my concept. So what is the benefit of this paper? First of all, I do have a standardized approach that I now can optimize. And it's an approach that does not require any additional effort to be taken into action. So still, I don't have any programming. I still have just the trainer who is setting up such a training within minutes usually. And yeah, no other knowledge. And I can just put in new BIM data, new CAD data. The training time with this concept is significantly reduced. The motivation is significantly increased without affecting the other target values. So the outlook or the future steps, the future works. When I did this paper, I didn't do the experiments with competing technologies. We did that by now. So we had further experiments with this software in cooperation with Mercedes-Benz, a German car manufacturer. We used augmented reality. We used a self-programmed desktop app and also a mock-up and compared training times, again with pretty impressive results. And of course, we want to applicate this software in further industrial use cases. So that's basically my presentation. Thank you for your attention.